Hi everyone, the final quantum talk of the day, so let's get through it. Another 20 minutes and then you're free to go to lunch. I'm Jasper and I'm going to present Synthetiq fast and versatile quantum circuit synthesis, which is a work I did together with Anouk, Benjamin and Martin. Now, if you've got this far into this quantum talks, I'm assuming that you already know what a qubit is. If not, let me remind you, of course, qubit is the quantum equivalent of a bit, either 0, 1, or any linear combination of both. What is important for this talk, though, is that you can also represent it as a vector. And this vector representation we will use in our circuit synthesis method. Now, for 2 qubits, this generalizes pretty straightforwardly. Instead of 2 states, you have 4 states, and your vector representation consists now of 4 numbers, all complex. Now, in quantum computers, you of course want to apply operations on these input states, and the way we do that is using operators. So operators are simple functions that go from one state to the next state. In this example, we have k qubits, and then your input representation is of the form C2 to the k. As a simple example, the Hadamard gate, when applied to the 0 state, gives a combination of the 0 and 1 state, and applied to the 1 state, the same, but with a minus sign. Now, what is important about these operations is that they are linear, and thus we can represent them much more easily with a matrix. And the way to read these matrices is essentially, if you look at the first column of the Hadamard gate, that is the output that you get when you input the 0 state. The second column is when you input the 1 state. So we can simply represent the operations or the operators, what they do on input states, by a matrix multiplication, multiplying them with the vector representation. Now, we're not quite there yet because we cannot tell our quantum computer to implement arbitrary operators. Why not? Well, quantum computers only have a limited gate set that they can natively execute. A very common gate set is the Clifford+T gate set, which consists of these gates. The Hadamard gate I already showed you. Then you also have the S and the T gates, and finally the C0 or the CX gate that is applied to 2 qubits. So these are the only gates that we can natively execute, and this of course leads to circuit synthesis, which means that we need to convert our operators into circuits that we can actually execute on quantum computers. So for example, suppose we have this very simple operator. We make it into a circuit that first apply a Hadamard gates, then a C0 gate, and then another Hadamard gate on the second qubit. So the problem statement we get here is, given an operator specification U, synthesize an efficient circuit. Now, this is not exactly what we wanted to tackle with Synthetiq. As mentioned in the title, we wanted to be as versatile as possible, and there are actually problem statements in circuit synthesis that are not captured by this statement. And there are 2 aspects that are still missing here. The first one is approximate synthesis. So because you only have a finite gate sets, there are infinitely many operators for which you cannot find a finite circuit that implements this operator. So the way to approach this is to approximately implement them, allowing for some distance that is not 0, but can be up to epsilon, which is some number. For those that are interested, this distance metric is usually of the form related to this, which is the Hilbert-Smith distance. But what it is exactly isn't important for this talk. So adding this first element to our problem statement, we're now not only given an operator specification U, but also a maximum distance epsilon. The second missing component is partial specification. And what does partial specification mean? Well, some applications in quantum computing do not require you to specify each entry in your matrix specification. So when you do full specification, that means that your entire matrix, your entire operator is specified, and each element in this matrix is important. However, you can also have isometries, where you only care about specific columns and you do not care about other columns. When does this happen? Well, for example, in state preparation, you know that your input qubits are in the 0 states, and therefore you do not care what your operator would do if you had any other input states than the 0 state, which corresponds to this matrix here. The reason that you want to do this instead of full specification is, 1, it's easier to specify this as a user, but 2, it's also more efficient to implement. Here, a very trivial example, of course, but even though our CCX gate is not the identity gate. Our isometry here can be simply implemented using identity. Of course, not very practical, but in this case, it's like this. Of course, you can also have just full partial specification, which means that you don't have just rows and columns that are specified or not specified. You can have arbitrary elements that are underspecified. And a use case here is relative phase operators, which you can see when you apply Boolean matrices or Boolean operators to your circuit. So Boolean operators is the CCX gate, which only consists of 0 and 1s. And relative phase operators essentially mean that you want zeros in the same position, but you do not really care if it's 1 minus 1i minus I that is in these non-zero positions. And oftentimes you can replace these Boolean operators with their relative counterpart while maintaining basically your entire algorithm structure. Even though these relative phase estimators operators have a more efficient implementation. So how do we specify this? Well, we specify this with two matrices instead of one. One is our original specification U. Another one is a Boolean matrix, and this Boolean matrix basically indicates which elements you want to specify and which elements remain underspecified. And if you want to give this into your computer, you basically say U on the question marks 1 minus 1 doesn't matter. Our algorithm doesn't look at this. So we get our final problem statements. Given an operator specification UM and a maximum distance epsilon, synthesize an efficient circuit. Now, how can we approach this? Well, the problem is that prior work looks at very specific gate sets, looks at very specific exact synthesis or approximate synthesis, so we couldn't really use the optimizations that they used in their algorithms in this very generic problem statement. But what we did notice is that simulated annealing is actually a pretty generic, simple algorithm that works perfectly for this problem statement. In simulated annealing, if you don't know what it is, you essentially keep perturbing your input circuit or your circuit to get closer and closer to your specification until you finally got it. So what does this mean? Well, here I've written a very simple implementation of simulated annealing. You first have some initial circuit C and some parameters, our epsilon and our specification. You check if your distance is smaller than epsilon. If so, you found your implementation. If not, you mutate your circuit, and then you probabilistically accept your new circuit or not. When you accept it, well, you definitely accept it if your distance becomes smaller, because that means that you're getting closer. But you also want to accept it if it's only slightly worse than your original circuit, because essentially you want to get rid of these local minima that you can get stuck in, and that's why you also want to get out of there. What makes simulated annealing also very applicable in this situation is that it's very parallelizable. So it's very scalable to more qubits or more gates this way. There are two things that we have to specify still in this algorithm. One is this distance function, and for that I'm going to refer to the paper because those are messy details that we don't really care about here. The other one is the mutation that we do, and the mutation is very simple. Suppose we have a circuit C. We either apply deletion of a gate, we swap a gate, or we add a gate. Those are the three operations allowed, and this way you can basically form your mutations. Now, the problem with simulated annealing is that it doesn't lead to very efficient circuits. Like these random perturbations, there are lots. If we apply this straight like this, it leads to crazy simple optimizations that you can do in your output circuit that you really want to get rid of. So what we do is a very simple simplification algorithm. We could also have used Quarl or any other resynthesis tool, but we noticed that this simple tool was good enough. And what does it do? Well, given our output circuit that implements our operator, we simply swap or replace gates that are replaceable. In this case, two Heidelberg gates after each other are just an identity gate. Then we swap the T and the S gate because they are swappable, so why not? And then finally, again, we replace the two T gates to a single S gate because that works. And then we keep doing this until we finally get our optimized circuit in the end. Okay, so let's take a look. Synthetiq is what our algorithm is called. We support any finite gate set, any optimization objective, incomplete specification, exact synthesis, approximate synthesis. And I hear you thinking, sure, you're very generic, but this cannot be efficient, right? Certainly you lose some efficiency, you lose some speeds in order to implement all these specific applications. Well, let's take a look. And here in the presentation, I'm going to compare to one other baseline that we compared against, which optimizes for Clifford+T T-depth, which is basically the amount of T-gates you have to execute sequentially. And they only do exact synthesis. And what do we find? Well, it's over the board a bit, quite a lot, from no speed up to 10 to the power of 4 speed up. But on average, or the median, is 2 orders of magnitude speed up that we actually reach with Synthetiq. So even though we have a very simple algorithm, we seem to be outperforming this baseline. And what this plot doesn't show is that in 30% of the cases, Giorgio times out while we can still find a circuit. What it also doesn't show that in 80% of our circuits that we tested on, we find more efficient circuits than Giorgio finds, and in the other 20% we find the same circuit that they do. Okay, we also want to apply Synthetiq in practice on actual circuits. So we applied it on 5 operators that we found are relatively interesting in practice. And we find that either Synthetiq in a reasonable amount of time, at most 8 hours, can find more efficient circuits than prior work or prior best effort things. So what we did for this previous best is we looked through papers, we tried to apply several algorithms to see which one works best, and then reported this. And with Synthetiq, we can simply do this all automatically, and we either reduce the number of OOPSLA, which is the number of helper qubits that you need to implement the specification, or the T-depth of the circuit. So in conclusion, we looked at this problem statement, which is very generic, with the operator specification UM and a maximum distance epsilon. We used simulated annealing to solve it, and we found that in practice we get more efficient circuits. Thank you.
Question session?
Thank you for the talk, very cool. So it seems from your specification that you can recompute M from U, is that correct? And if so, why do you actually need M in your spec?
Yeah, so that's a very good question. So basically the reason that I showed this U and M is because that's the way we implement it in code. Like in code you cannot specify question marks. So in the code how this works is that these question marks are basically zeros, and then this M we use additionally to show like, yeah, these zeros are zeros, but you can do whatever you want there. So essentially that's why I showed this with question marks. But yeah, if you are able to work with question marks in in your code, then you would be totally fine, and then you wouldn't need M.
Very nice. Your examples at the end, I think they have like 4 qubits or 5 thereabouts. What's actually the kind of the limit that your tool can handle in terms of number of qubits?
Yeah, so like it depends both on number of qubits and number of gates in your circuits. So we found that for 4 qubits, which is the use case we look at most, we can get to around 30 gates at most for like a reasonable amount of time you would need to implement this. From 7 qubits, you get out-of-memory errors because we store these entire matrices which become very, very large. And for 5 and 6 qubits, basically you get to very low gate counts that you can implement. So I think the largest I implemented, I tried at some point, is like 3 or 4 gates for 6 qubits and 5 or 6 or 7 gates with 5 qubits.
Is this stuff very parallelizable so that like GPUs might have a chance to do better here?
It's very parallelizable in the sense that you can do simulated annealing, like you can do multiple runs at the same time. I don't think, because GPUs would help if you can do this matrix multiplications that we do for like getting the circuit that is within one simulated annealing one, and I think there it could also help if you implement these matrix multiplications on GPUs as well, yeah.
Thank you for the great talk. Have you explored whether there are cases where simulated annealing performs worse than on average? Like, have you done any worst case analysis? Are there surprising outcomes
So we didn't do worst case analysis, but you can kind of see here in this plot already that like there are some cases where we seemingly not outperform prior work. So there does seem to be cases where Synthetiq doesn't really directly like find it more efficiently than prior work. And I looked into this and I was wondering like how does this happen? And I couldn't really find a reason why it wouldn't work for one case or another case. One interesting thing I noted though is that the more qubits we had, the better our approach became compared to prior work. So essentially for one qubit, I looked into approximate synthesis for one qubit mainly, and they were the same compared to prior work. Well, the more qubits, like 2, 3, 4, you get better and better and better. And the reason for this is because of these distance functions that we use. And for one qubit, it doesn't really give that much information. So this distance function shortly is based on this Hilbert-Schmidt distance. And as you can see, because we only apply one new gate in each thing, we can only change parts of your part of the matrix. Because some elements will stay the same if you only apply a Hadamard gate to the third qubit or something. But if you have only one qubit, then basically every new gate that you apply changes the entire matrix. So then I found that in this case, this distance metric doesn't work that well. And like, yeah, that's one case where Synthetiq kind of fails in some sense.
That's very interesting. Thank you.
So I have a question. So
Yes.
Have you actually tried other gate sets? Because I guess you're only showing one gate set that is
Yes.
the gate set, but how about other gate sets?
So in the presentation, I indeed only included Clifford+T gate set. In the paper, we also compare against a tool that can also handle other gate sets. And there we see basically the same kind of performance improvements as we had compared to the Giorgio baseline. So yeah, we did do this, and we did see that in this case we also get a significant improvement.
I have another question. It's like this. Okay, so because you are actually giving a unitary and then to synthesize the circuits for you. This I understand. But I guess. Based on my experience, I guess the most need for you are giving a unitary and then going to synthesize the really circuits. Basically, you are dealing with some of this Hamiltonian simulation that simulate a very large like a system that you actually expect you have 100 qubits. So have you actually thought about how you actually can parallelize the computation of, let's say your unitary is it's talking about 100 qubits?
So how to extend this approach to more than 5 or 6 qubits? Yeah, this is very hard. Like there are several things that you would need to do to make this even remotely applicable to this setting. Is one, you have to get a more efficient, not implementation, but way to represent these states, because full matrix specification doesn't work when you don't work with 100 qubits. That's way outside of the scope. So this you would somehow have to change that. For partial specification, this is very hard because these question marks are in random positions, so you would somehow need to do this more appropriately, and I couldn't find a way to do this. A second problem when you go to 100 qubits or more is that the amount of options that you have for mutations are getting extremely, are just getting too big to basically handle. So I think for when you want to go to 100 qubits, Synthetiq is not the best approach because this random search is just not going to work. There are too many options. Either what you do is you try to decompose in smaller and smaller circuit. So you decompose your 100 qubits operation into maybe 5 qubit operations, each one that you don't know how to implement, but it works to synthesize it like this. And then you use Synthetiq to do these 5 qubit ones. The problem there is what do you use to get from 100 to 5? And there are several algorithms that can do this, but they're just not very efficient. They generate a circuit like the Vechev, I always forget the name, the Vechev-Kolomov algorithm does this, but it's just very, very inefficient to do something like this. So there, it's kind of a trade-off how you want to approach this for larger operators.
Thank you, thank you.
Oh.